Last week we defined the derivative and derived some rules to make them easier. The derivative of the function gave us the slope of the graph of a function at various points. And while this may be interesting, I'm sure many of you are wondering, what's the point? Why do you need to learn this? Today we're going to go through a number of applications of this idea that are not just about lines, curves, and graphs. First things first, let's change our independent variable. So we've been using x most of the time. We'd have functions of x, but we're going to change x to t in a lot of these examples. We'll use x on some of them as well. But here, t is going to represent time. So we're going to have some function f of t, which basically represents some value, some quantity that changes over the course of time. Now, the simplest example of this is something like distance. If an object is traveling, we can model its distance by a function of time. So let's say we have some object, be it a person or a car or anything, that starts at some point A and travels to some point B. We can set up a function, and here it's actually common to use s instead of d for distance. Mostly that's because a d would conflict with the notation for derivatives. What we had dy dx for our derivatives. And this d here, we conflict with a d for distance. So generally we'll use an s here. Though we'll also use it for some other functions as well. Use other letters for other functions. But we have some function, so at say time t equals whatever, we're at some other point along here, and the distance from A to that point is given by this distance function. Now, for example, for an example's sake, let's go ahead and say we're just going to use s of t equals t squared. It's an easy enough function to work with for now. T here is what we're going to take in hours, and we're going to assume that A and B are 4 miles apart. So the total distance here is 4 miles. Go ahead and write that information down so that we can reference it later. So the distance from A to B is 4 miles, and our distance function is t squared. That means that after 1 hour, so at 1 hour, we've gone 1 mile. After 2 hours, we've gone an entire 4 miles. And basically saying here that it takes us 2 hours to get from A to B, because that 4 miles there agrees with the distance from A to B. But now we can ask the question, what was our speed? How fast did we go from A to B? Well, over the first hour, we went 1 mile from our 0 miles that we started with. So if we started at A, that was at time t equals 0, and we had gone 0 miles at that point. But then by the time t equals 1, after 1 hour, we've gone a distance of 1 mile. So 1 mile minus 0 miles over 1 hour minus 0 hours. And we have 1 mile per hour. But if we look at the whole thing, if we look at what was our speed once we've gone from A all the way to B, well, now we've gone 4 miles minus our 0 hours, divided by the 2 hours that we took, minus 0 hours, and so went 2 miles per hour over the whole distance. What we're doing here is finding the average speed. We didn't use a constant speed over this entire time period. We're computing an average over a time period. In other words, we can write that out as average speed is our change in distance divided by a change in time. You might think of speed as distance over time, but keep in mind that if we're using different points along this path, then we want to actually specify that we can change which interval that we're working with. Now this formula should be actually kind of familiar to you. This is the same formula that we use for slope. Remember, slope is a change in y divided by a change in x. Now we're using different variables here, so change in time would be a change in t instead of a change in x, and a change in distance, that would be a change. That'd be, you could say, a change in s or a change in d, depending on what you actually want to use for your letter there. But it's the same formula. And that means that if we're essentially wanting to work with average speeds, we could essentially just look at the graph of the function. In this case was t squared, and find slopes of secant lines. Let's go ahead and actually graph this. So I'm going to say some function s. I'm going to have to use x here because GeoGebra assumes that our independent variable is x, but just keep in mind that we have to do that. I'm also going to use an if statement here just to only look at the part, look at x values between 0 and 2. But then our function here is x squared. So this is a graph of the distance we've traveled over any given time. So after an hour, we only went 1 mile. After 2 hours, we went the entire 4 miles. And you could say, if we look at, let's go ahead and actually put some points on here. So we start at 0, 0. That means at time 0, we've gone 0 miles. Then we have 1, 1. After 1 hour, we've gone 1 mile. And then we have 2, 4. After 2 hours, we've gone 4 miles. If we go from A to B here, these are not the same A and B that we were using before. These are just points on our graph. But this line here, this line has a slope of 1. It's saying that our average speed over this 1 hour is equal to 1. That's our slope. But if we look at the line segment from A to C, this line actually has a slope of 2. The average speed over those 2 hours is 2. So basically our average speeds are our slopes of secant lines. Now that might not be what you're looking for though. What if instead we want the actual speed that you're traveling at time t equals 1? So what would your speedometer be reading if this is, say, a car traveling? Now, of course, this is kind of a slow speed for a car, but that's what we're trying to get at. What would be the actual speed you'd measure for that object at that time? Now, we could take average speeds over smaller intervals of time. We could say, look at just, I don't know, let's pick another point that's really close on here. And actually, let's get rid of these names. They're kind of getting in the way. Get rid of the labels. So if we pick a time that's much closer to 1, then we could look at the secant line. Come on, select that point. There we go. We can look at the secant line there and look at its slope. Its slope is definitely different from the slope that we had from that over that entire first hour. And it should be closer to what your actual speed at time t equals 1 should be. Now, we're not really calculating that right now, but that's the idea that we want to take for to find that actual speed. And then to really get in there, we would need to then keep shrinking that time period down smaller and smaller. Essentially, we're taking a limit here. And really, this is exactly what we did to find derivatives back in section 2.1. To find, basically, our speed at time t equals 1 should be the slope of the tangent line to this curve at 1, at t equals 1. So you can say here, whereas we looked at the average speed, we can then also look at what we call the instantaneous speed. And that's going to be the derivative, because we use derivative to find the slope of tangent lines, of our distance function. So in our particular example, remember our s of t was t squared. That was what our actual distance function was. We know how to take the derivative of t squared. If you don't remember, this is a power of t, or you could say a power of x if we were using x instead of t's. But we bring down that power of 2, and then we reduce the power of 2 by 1. Of course, t to the first power is just t. So our derivative here is 2t. That means that, say, at time 1, our speed is actually 2 miles per hour. We're actually traveling at 2 miles per hour exactly at the point t equals 1. We could even go ahead and use that slope of 2 and show that we actually, at t equals 1, we do have that actual tangent line with a slope of 2. But at exactly 1 hour, the object was traveling at 2 miles per hour. Of course, it started at time t equals 0 at 0 miles per hour, just plugging 0 into this formula. So over the course of that hour, it sped up from 0 miles per hour to 2 miles per hour. But on the average, over that entire interval, it was going 1 miles per hour. That's the kind of idea that we want to get across. Now, of course, we've been doing all this with a function that represents distance. Our function doesn't have to represent distance. It can represent any other quantity that changes over time. It could represent, say, the amount of water that's being poured into a tank, or the outdoor temperature over the course of the day, or even the population of a city over the course of a decade. Any sort of one of those is a quantity that changes over time. And we can talk about the rate of change of that quantity. So let's say we have a function f of t. This is some quantity that depends on time. And we can talk about the average rate of change of this. Over some interval of time as the change in our function divided by that change in time, how long that time interval was, which we could also write as delta f over delta t. Remember, the delta here is a notation that means a change in whatever variable we have behind it. So basically, we take the amount of time that we have for our interval on the bottom, and on top we would subtract whatever the value of f is at the end minus the whatever the value of f was at the beginning. But then we also have the instantaneous speed, or not speed, but rate of change. this is just going to be the derivative. Basically f prime of t. And in some situations, it can be very beneficial to work with this derivative. Let's go ahead and actually work on some problems to show this in action. I'm going to work on this problem right here. This is a problem I've taken from a different edition of the book, so this is not going to be the same problem as you'll see in your textbook. But it is the same kind of idea as you might see in maybe something like... Actually, I guess 17 is... Okay, in this particular case, it is the same as the one in the textbook. That won't be the case for some of the other examples I'm going to work on. But this is problem 17 from this book. But we're taking a silver dollar and we're dropping it from the top of the Washington Monument. Probably don't want to actually do that, but this is the idea that we're really getting at here. When we do that, we have a formula for the distance over time. Now here they're actually talking about the distance as being height above the ground. So actually we're not starting at 0. When we put in 0 here, we actually start at 555. I assume that's what the height of the Washington Monument is. And then we might, when it actually hits the ground, it would be at a height of 0. But the idea is still the same. How this distance changes over time will be reflected in our derivative, and we can get the average velocity, which is another term for speed, using this distance function. So, part A, we want the average velocity using this function over the interval from 2 to 3. Of course, that just means that we're going to take the value of our function at 3 minus the value of the function at 2 divided by 3 minus 2. This is our difference, our s values at the endpoints of this interval over the difference in our t values. Our t values going from 2 to 3. Now, of course, we do need to find out what s of 3 and s of 2 are, and we need to use this formula for that. So s of 3 is minus 16 times 3 squared plus 555. Go ahead and use a calculator for these. That it's not really worth trying to do everything by hand here. Turns out we get 411. S of 2, the same thing, but with a 2 instead of a 3. Again, using a calculator, I got 491. So what this is saying is that at 2 seconds after we've dropped it, it is 491 feet off the ground. 3 seconds after we've dropped it is 411 feet off the ground. Our average velocity then is 411 minus 491 over 1, because we're only doing it over 1 second. And so we get negative 80. Now, we do want to give units to this. The average velocity here, we're subtracting feet on top, and we're subtracting seconds on bottom. So this is minus 80 feet per second. And note here that we do have a negative because the actual height is decreasing. The silver dollar is dropping. It's closer to the ground at the end than it was at the beginning. So it's moved, well, basically over the course of that 1 second, it moved 80 feet. Now we want the instantaneous velocities. Basically, we're going to take our distance function and we're going to differentiate it. The derivative of minus 16t squared plus 555. Of course, here we have t squared. Remember, when we differentiate a constant times t squared, we just differentiate the t squared and multiply the answer by that constant. Well, we already saw that t squared becomes a 2t. That means we get a minus 16 times 2t. And then differentiating the constant of 555 gives us a 0. Because constants always become 0 when you differentiate them. Well, we can go ahead and simplify that. We have 16 times a 2, so we have a negative 32t. And that means that at t equals 2 and t equals 3, if we just go ahead and compute those, s prime of 2, we have negative 32 times 2, or negative 64. Now this is a derivative, but we can compute the derivative by remembering that it is a limit of these velocities. Velocities were feet per second in this case. That means our derivative is still in feet per second. S prime of 3, same idea here. Go ahead and plug in 3 into our formula. We have negative 96, and again, still feet per second. So at the beginning of this interval from 2 seconds to 3 seconds is traveling at 64 feet per second towards the ground, and at the end of it is traveling at 96 feet per second towards the ground. On average, it was 80, but it was going at a slower speed at the beginning than it was at the end. Continuing on, we can do part C. Part C, they're asking how long will it take the dollar to hit the ground. So we have to interpret what that means in terms of this function. Basically, what do we know about what's happening at the ground? Well, we know there the height is equal to 0. And that means we're looking at what t value gives us an s value of 0. Basically, when is negative 16t squared plus 555 equal to 0 feet? If we go ahead and solve for t, of course here we have 16t squared is equal to 555. These two have to be equal to each other if their difference is equal to 0. We can divide everything by 16. And then take the square root. Go ahead and stick that into a calculator, and we get 5.89 seconds. That's a little bit rounded. So actually rounded up a little bit. That means that after approximately 5.89 seconds, this silver dollar will have hit the ground. Started at 555 feet in the air, and now it's down at the bottom after that amount of time. But then what they're wanting us to do is find the velocity of the silver dollar when it does hit the ground. Basically, at this time, what speed is it moving? That means we're going to plug that into our formula for our derivative. So negative 32 times that. And I got negative 188.47 feet per second. And note that this value is actually kind of significant. How hard the silver dollar does hit the ground depends exactly on how fast it hit the ground. And that requires us to know what that instantaneous velocity is, and not just the average velocity. If I calculate the average velocity over this entire nearly 6 seconds, it's not going to tell me how hard it hit the ground, because it's going to give me actually a much smaller number. So that in certain applications, I definitely need to know this instantaneous velocity and not just the average velocity. But the whole idea of how we actually derive all this stuff is just use derivatives. Everything that we've done with derivatives so far, we can use here to actually solve various problems. And everything that we come across throughout the rest of the course will also be allowed to apply to these problems. And that makes the derivative quite useful. Let's try another problem. So here, problem 34, this actually is not in the book this time. I know that for sure. The equivalent one would be problem 35, which actually talks about the population of Australia. This one's talking about the population of Japan. Same kind of problem, but different numbers and all that. But the population P in thousands of Japan can be modeled by this formula. It's a quadratic, but that just helps us actually take the derivatives later on. Note here that T is time in years, with T equals 0 corresponding to 1980. So basically, T is the time is the number of years since 1980. We're going to evaluate our population formula for 5 different values, and then we're going to talk about what those actually mean. And we'll eventually also compute the derivative at those values. So I'm actually going to put those into a table here. So say time t, we'll have the population p, and we'll eventually have the derivative at those t's. And we're going to look at t equals 0, 10, 15, 20, and 25. Well, all we're really doing is asking what is the value of p at those t's, and I'm just using this formula. Of course, plugging 0 in is actually pretty simple. These first two terms go away, and we're just left with this 117,216. Then I plug in 10. So again, just use a calculator for this. It's by far the easiest way to tackle it. So I have negative 14.71 times 10 squared plus 785.5 times 10 plus the same 117,216. When I plug that into my calculator, I get 123,600. Then I do the exact same thing with 15, 20, and 25. And I'm going to walk through each one of those. For 15, I got 125,689. That's actually slightly rounded. These two are exact, but this one had to be rounded up slightly. I think it was like 688.75 or something like that. For 20, this was another exact one. I got 127,042. And this one I round up slightly as well. So this was 127,660. Now note that these represent thousands of people. So actually, in 1980, we're talking about 117 million people. When t equals 25, keep in mind that is in 2005. So that's 1980, 1990, 1995, 2000, and 2005. So in 2005, we're talking about a population of 127 million people. Though, I mean, technically here in 2000, we were also talking about that as well. Now we have to actually look at the thousands of people as well. Now we need, in part B, we need to determine the population growth rate. They're basically asking us, what is the rate of change of population? How fast is the population changing over the years? And we're going to find that using a derivative. And we're using the dp/dt kind of notation here. Instead, this is the same thing as p prime technically, just a different notation. But we're taking this formula here and we're differentiating it. Now this is a polynomial. We take it term by term. We start with the negative 14.71 times t squared. We take the derivative t squared. Of course, we've done that a couple times already in this video. So that becomes a 2t. Then we have the 785.5 times the derivative of t. Derivative of t is just 1. And then finally, the derivative of this constant value at the end is just 0. And we can go ahead now and actually just expand this out. So we take the negative 14.71 times 2. We get a negative 29.42t. And then this is just being multiplied by 1, so we just leave it as a 785.5. That is our formula for the population growth rate. In part C, they want us to use this formula we just got and put these same 5 values in it. So, for instance, at t equals 0, I just get this 785.5. When I plug in 10, I get, well, now I actually have to compute it what it is. And again, I just use a calculator for all this. So for 10, I got 491.3. For 15, I got 344.2. For 20, got 197.1. And finally, for 25, I just got 50. This one actually came out nice and exact. Now, what do these actually mean? These numbers tell us how much we should expect the population to change from a given year to the next. So in 1995, we know that the population was 125 million people, or 125.689 million people, if we want to be more precise. But we expect the population in 1996, the very next year, to be essentially 344,000 more people than what we had in 1995. So we would expect that P of 16, so 1996 would be t equals 16. We'd expect that to be the 125,689 plus 344.2. Or I guess we can leave off the 0.2. We'll round up, or I guess round down. But we expect an answer of 126,033, or 126,033,000 people. Now that actually won't be the exact number that you'll get if you plug 16 into the formula. In fact, we can go ahead and do that. If I just take out my calculator here and go ahead and just plug these numbers in. So I'm going to actually start with the constant that will help me just subtract from it. So that constant times, or minus 14.71 times 16 squared, I'm just going to multiply 16 twice in there, plus 785.5 times 16, and the exact value of P at 16 is 126,018, if I round it off. So not exactly the right number, but it is pretty close compared to, we're talking, we had a change in over 300,000 people, but our estimate was actually much closer than that. It was only on the order of about 15,000 people. So this essentially gives an easy way to approximate the actual amount of change without having to do all the calculations for every single point. And there's actually other applications that we'll get from having this derivative. We can talk about, I don't want to get too much into it, but we can talk about whether or not things are increasing or decreasing, and a lot of other stuff like that. We'll get into more applications of derivatives in chapter 3. But for the moment, what we're basically saying here is that we can treat derivatives as a way of getting these rates of change. And that is a very useful concept in a wide variety of applications. Now, that's not the only application that we have for derivatives. We're going to look at another one in the next video. So I'll see you there.